I'll try to explain the hypothesis testing method in the easiest way I can. Please stay focused until the video ends. Imagine you're hired by a company that's selling bottled water, and this is your first day at work. You said hello to your new boss, but the boss says he doesn't have time for chit-chat. Well then, let's get right into it. The boss says the machine should dispense 50 milliliters of water in a bottle with roughly plus minus 0.5 milliliters of 1 standard deviation error. So what does plus minus 0.5 of 1 standard deviation error mean? It means 68% of the bottles will have the amount of water in between 49.5 and 50.5 milliliters, right? Because that's the plus minus 1 standard deviation. So here on the machine, it says the average value is 50 milliliters and the standard deviation is 0.5 milliliters. Okay, the boss continues. You'll sometimes find bottles that have greater error amounts, but it's okay, as long as most values are within plus minus 0.5 milliliters of error. So he's basically referring to 68% as most. By the way, you shouldn't be favoring words like most, little, or few, because those are not quantitative descriptions. Like someone could refer to 99% as most, right? So that boss should have chosen a better word. But at least he did say that plus minus 0.5 corresponds to the 1 standard deviation, so anyway. He says your job is to monitor this process and make sure the machine is running properly. So that's gonna be your task, okay? Then he tells you to call him if the machine starts acting weird. But here's the thing, he's warning you. You better make sure though that you're 95% confident about that situation before you call me. You do not want to waste my time. Okay, that sounds a little mean, but let's get to work. After some time, you notice that many bottles are not filled with the proper amount. You see these values? The numbers don't look that good. What do you think? You decided to randomly collect 35 samples. The average value was found to be 49.7 milliliters, but that's within the range of 1 standard deviation error. So are we good? Should we just keep running it? No. That could simply be your subjective judgment. So we should investigate this statistically. The boss told us to call him when we are 95% confident about the situation. Alpha is what we call significance level in statistics. 0.05 means 5% of uncertainty, and that means 95% of confidence. This is the standard normal distribution. If you don't know about this distribution yet, I suggest you to first watch my other tutorial videos about z-score and standard deviation. So I'll assume you already know this. As we know, the 95% region is in between the z-scores of plus and minus 1.96, right? So if your z-score is within this 95% range, you could say that the machine is running properly. Because the 50 milliliters is like at the center, and you're pretty close to the center. But if your z-score happens to be outside of that 95% region, then there's something wrong with the machine. You've seen this z-score formula, right? You had a sample data, so instead of the population version, we are using the sample version that has this dividing by square root of n. Let's plug in our numbers. We got about minus 3.55. Oh, that is outside of the range. We are now 95% confident to say that the machine isn't running properly. We could call the boss for help. So I'll match the terminologies now. Alternative hypothesis was the error region, and null hypothesis was the 95% region. The 35 samples that we had as data rejected our null hypothesis by giving the average value of 49.7 milliliters. So, why does the z-score test with samples use population standard deviation divided by the square root of n, instead of just the population standard deviation? Let's bring our values again. If we just used the population version, which doesn't have the square root of n, we would have gotten negative 0.6. Now here's the thing. Imagine that you were actually using only 10 samples before, not 35 samples. Then with the population version, you would still get the same value. Then what's the point of having many samples if the results are the same? Don't you agree? What's the point? Moreover, it's below 1.96, so you'll be thinking that the machine is working fine when it's not. Now let's try to use the sample version. Okay, minus 1.9. Now the number of samples does affect the result. Minus 1.9 is within the range, but you could be thinking that perhaps 10 samples were not enough. If you use more samples, your z-score will become more vulnerable to escape the region. Can you imagine that? Let me show you. See? The more we test, the more difficult it'll become to hide the truth, which is its malfunctionality. So this is the reason why we need that term included when taking sample data. Now, the boss finally arrived after your call. He is not content, because he only took 35 samples. He decided to take 15 more samples by himself and average the amount. It was found to be 49.88 milliliters. Yes, so here when we increase the number of samples, the average value should most likely have changed as well. But before, I was just wanting to explain you why we are putting the square root of n, like how it could affect the z-score, so please know that. Anyway, back to here. So now the average value has slightly changed. Let's do the same thing. You get minus 1.69. It seems the machine was working properly. Then why did we get the wrong result before? Like, we just learned that as we take more samples, the value should be starting to escape from the region. Why did it go back in with more samples? This is the case when it was just the machine that isn't working accurately enough. They just have a low quality machine. It's not our fault. So this being known, you can imagine how low quality machines would need many samples to confirm errors, when high quality machines don't need many samples to check. You could take many samples, but the results will be quite consistent. Make sense? Thank you for watching this video, and I'll hope to see you next time.